Hi, Honors Algebra 2 students. In this lesson, we are going to finish up our topic of solving systems of linear equations algebraically. And then in the second part of the lesson, we're going to start discussing function notation. All right, so as you can see, I have this first example already written out. So you may want to pause the video and get it down in your notes, and then you can follow along more easily as I talk through it. Okay, so our instructions say solve the following systems of equations algebraically, then determine whether the equations in the system are independent, dependent, or inconsistent. And one thing I want to emphasize is that we will always first solve the system of equations, just like it says. And then once we've solved the system, then we'll make that determination on if those equations in the system are independent, dependent, or inconsistent. In other words, after we solve, we will determine based on the solution what type of equations are in that system. All right, so in the first example, there are many ways in which we could solve this. In fact, your textbook shows an alternative method for solving the system of equations. So if you're interested in looking at that, you could simply go to our textbook and go to section 4.2, and you could look up an alternate solution. I have found, though, that when I go through this example with students in class, they typically solve it the way that I showed, so I figured I would show that part in our video. So we've got a system of equations in the first example. As you can tell, though, it looks a little different because our variables are in the denominator. All right, you can still, though, approach it either with substitution or elimination, and I will tell you, I stay away from substitution method unless I have a coefficient of 1 or negative 1. So that's going to be true in all of the examples that we look at today. We actually don't have a coefficient of 1 or negative 1 for either of the variables in either of the equations. So we're going to use the elimination method for all of our examples in solving systems today. So in the first example, if I multiply the top equation by negative 2, I'll get this equation right here. Just distribute the negative 2 to the 6, to the negative 7, and to the 8. And obviously our denominators will stay the same. And then I just rewrote the second equation right here. And then I'm going to add those equations together. And as such, my 14 divided by y and my negative 14 divided by y cancel out, so that y variable is eliminated. It gives me the ability to then just work with my x variable. So negative 12 plus 15 gives me 3, and my denominator will remain the same. That's what happens when we add or subtract fractions and they have a like denominator. We add or subtract the numerators and leave our denominator the same, which is what I did right here. And then 21 minus 16 will give me 5. If I go through and cross multiply, I get 5x is equal to 3, and then I get x is equal to 3/5. All right, now I could plug this 3/5 into either the top equation or the bottom equation, or in fact even my new equation right here, and I could continue on with solving for y. But some of the examples we've done recently, it might be just as easy, or in fact even easier, to start over and eliminate the other variable by way of starting the elimination process from the very beginning again. So that's what I ended up doing. And again, it's personal preference, and in some cases, I suppose it's easier to do one or the other, but in some cases, it's just personal preference. So what I decided to do was I rewrote my original system of equations again, and then this time I needed to focus on eliminating the x variable. So I multiplied the top equation by negative 5, so I would get a negative 30 divided by x right here, and the bottom equation by 2, so I would get a positive 30 divided by x right here. Of course, I have to distribute the negative 5 to all the terms and the 2 to all the terms. So I'm going to get a positive 35 divided by y here and a negative 40. And then in the bottom equation, I'm going to get a negative 28 divided by y here and then a positive 42. Once again, I'm going to add these equations together, and the x terms go away. They cancel each other out. 35 minus 28 gives me 7, so 7 divided by y. Negative 40 plus 42 gives me 2. I cross multiply. I get 2y is equal to 7. So y is equal to 7/2. And indeed, then I write my final answer as an ordered pair. We always write our final answers as ordered pairs to a system of equation. equations. And also one thing I want to emphasize, even at this level of class, an ordered pair is not an ordered pair unless you have the parentheses around it and the comma in between. That's what makes it an ordered pair. In case you're wondering if I take off for that, I absolutely do. Every single time you don't write it mathematically correctly. All right, now that's solving that system of equations algebraically, albeit maybe the original system looked a little bit different, but we still used elimination method. Now, as far as classifying whether the equations in the system are independent, dependent, or inconsistent, this is the part that may be new to you. So if we get an ordered pair solution when we solve our system of equations, that is an independent system. All right, as we look at the next example, once again, I'm going to use elimination to solve this system because I don't have any coefficients, numbers in front of the variables, that are a positive 1 or a negative 1. So if I multiply the top equation by 2, let's say, and the bottom equation by negative 3, let's see what I get. I get 30x minus 24y is equal to 36. In the bottom equation, I get negative 30x plus 24y is equal to negative 42. If I add those equations together, the x terms go away, the y terms go away, so on the left-hand side I get 0, and on the right-hand side I get negative 6. So we know from working with a scenario like this in prior examples and lessons that if our variables go away and we have a false statement like we do here, 0 equals negative 6, our final answer is going to be no solution. So we can write those words, or if we want, we can use the mathematical representation of that. When we classify the type of equations that are in that system, if we have a no solution scenario, that's going to be an inconsistent system. And once again, we do our classifications after we come up with our final answers. All right, in our next example, we're going to once again use elimination to solve this system of equations because we don't have any coefficients that are a positive 1 or a negative 1. So if I multiply the top equation by a negative 3, I get negative 12x plus 9y is equal to negative 24. If I rewrite the bottom equation, and then if I go through and I do my adding of the two equations, my x terms are going to cancel out, my y terms are going to cancel out, so I get a 0 on the left-hand side of the equation. And then if I add negative 24 plus positive 24, I also get 0. So my variables have gone away, and I have a true statement this time. So my final answer is going to be an infinite number of solutions on the line, but I have to state the specific equation for the line. Now, I can go to the top equation and use it, which I'm going to do, or I could use the bottom equation if I wanted to, or I could even rewrite those equations in slope-intercept form, and I would find that they are indeed, they're the same representation in slope-intercept form. All right, as far as classifying the type of equations that are in that system, in this scenario, we're going to have that these are dependent equations in this type of system. So once again, we solve it first, and then we classify what type of equations are in that system. All right, so as a summary to solving systems of linear equations, we've looked at doing that algebraically, graphically, and now we're classifying the types of equations that are in the systems. So let's go through and do that summary before we move on. If, like in the first example that we did today, we solve a system of equations algebraically and that solution is an ordered pair solution. If we were to graph that system of equations, we would find that those lines would intersect at that ordered pair. And when we classify the type of equations that are in that system, those would be independent equations. If, like in the second example we did today, we algebraically solve and we get no solution, if we were to graph that system, we would find that the lines are parallel lines. And when we classify the type of equations that are in that system, they would be inconsistent equations. And then finally, in our third example today, we algebraically solved and we found that there were an infinite number of solutions on the line. Now we do need to state whatever the equation is specifically for that line, but I just wrote it generically down here. If we were to graph that system of equations, we would find that they represent the same line. And as far as classifying the types of equations that are in that system, they would be dependent equations. All right. In the second part of this lesson, we're going to talk about function notation. And this will give us an introduction to function notation, which we will continue to use in the next parts of this chapter. So in function notation, in these examples, we've been given that f of x is equal to 3x plus 11, and g of x is equal to x squared plus x plus 1. And we're going to use those function definitions that have been given to us to do some evaluation in the examples below. Before we get into that specific evaluation, though, I want to talk about the following. Sometimes students get really hung up on the fact that there's an x right there and there's an x here, etc. And they don't know what to do when they get expressions that are given to them instead of just x's, so to speak. So I want to just offer the following way of thinking about this function notation. This is saying f of something is equal to 3 times the something plus 11. Or g of something is equal to the something squared plus the something plus 1. Or sometimes you can even think about it as input value. So f of some input value is equal to 3 times that input value plus 11. Or g of an input value is equal to the input value squared plus the input value plus 1. In other words, whatever you're given right here, you're going to take 3 times it plus 11. Here, whatever you're given, you're going to take that given value and square it and add that given value again and add 1 to it. So just an alternative way of thinking about it instead of getting really focused on it just being an x, so to speak. All right, so the first example, we're going to evaluate g of negative 3. And I've got these kind of color-coded with the blue and the red in case that helps you see it a little more clearly, so to speak. So g of negative 3, our input value is a negative 3, or our something is a negative 3. So we're going to take that negative 3 and we're going to square it because we're using this function definition over here. And we're going to take that negative 3 and we're going to square it, and we're going to add a negative 3 to it, and then we're going to add 1. And then we're going to go through and we're going to simplify. So negative 3 squared is 9. And then if we go through and take 9 minus 3, we get 6, and we add 1 to it, and we get 7. So g of negative 3, we're going to leave the left-hand side exactly as is. G of negative 3 would be equal to 7. All right, next example, we're going to take f of 5. So we're going to go over to our function definition over here for f of x, and we're going to indicate then that we're going to take 3 times that 5, that's our input value, or our something, and then we're going to add 11 to it. And then in the denominator, we're going to switch back to our g of x definition. So g of 5 will be 5 squared plus 5 plus 1, because I'm going to switch over and use my g of x definition right here. And then we'll go through and we'll simplify. So we've got 15 plus 11 in the numerator. We've got 25 plus 5 plus 1 in the denominator. So we'll have 26 in the numerator and 31 in the denominator. Obviously, as a fraction, I can't simplify that anymore. Do not give us a decimal answer. So f of 5 divided by g of 5 is going to be equal to 26 over 31. All right, as we take a look at this next example, this is composition of functions. So it's read as f of g of 2. So it's a little bit like order of operations in that we're going to start in this innermost part first, and we're going to figure out what g of 2 is, and then we're going to work our way out to working with function f. So g of 2, we'll be using our g of x definition right here, and then when we work our way out, we'll be working our way out to the f of x definition right here. Okay, so I usually figure out what g of 2 is equal to first, as far as just writing that a little bit separately. You certainly have to evaluate it first, but I even write it out separately. So g of 2 is going to be 2 squared plus 2 plus 1, which will give us 4 plus 2 plus 1, which gives us 7. So I figured out this innermost part right here. G of 2 is equal to 7. So then I'm going to go and I'm going to say, okay, well, I'm now going to evaluate f of 7. So f of 7 says I take 3 times my input value of 7 and I add 11 to it. So f of 7 would be equal to 21 plus 11. And then if I went back to my original notation, f of 7 really represents f of g of 2, so I could rewrite it in that as far as my final answer goes, and that's going to be equal to 32. All right, before we get into the specifics of our next examples, I want to draw your attention to the following. We've got the same function definitions that we had in the prior examples, but notice in this first example, we're evaluating f of s plus t. S plus t is obviously an expression. So when we plug it into our function definition, we're not going to plug it in any differently, but our final answer will be in an expression. Our prior 3 examples, we were given numerical input values, so our final answer was numerical. Here we have an expression, so our final answer is going to be an expression. Remember when we plug this in, this says f of something equals 3 times the something plus 11. So when we plug that in, we're going to take 3 times the something, and we're going to add 11 to it. And then when we go through and simplify as much as we can, sorry, I'm having problems with my stylus right here. That's going to be equal to 3s plus 3t plus 11. And that's all that I can do as far as simplifying it. All right, in our next example, we're back to composition of functions. So this is read as g of f of x, and I'm going to do my work down here because I need a little bit more space. So I'm going to start inside here, and I'm going to replace that f of x truly with what f of x is equal to, which is 3x plus 11. Again, an expression in this case. So g of f of x, which is 3x plus 11, will be equal to, now I'm going to take, this is my something, and I'm going to plug it in here. So g of something is equal to the something squared plus the something plus 1. So the something just happens to be 3x plus 11. So I'm going to take 3x plus 11, and I'm going to square it, and I'm going to add 3x plus 11 to it, and then I'm going to add 1. And yes, I am going to go through and I'm going to simplify that. So remember, 3x plus 11 squared, don't forget, is 3x plus 11 times 3x plus 11. Just a little reminder right there. All right, so when I FOIL that, I'm going to get 9x squared plus 66x plus 121. And then I've got still the 3x plus 11 plus 1 from up above. And if I go through and do my final simplifying and go back to my original problem, g of f of x will be equal to 9x squared plus 69x from the 66x plus the 3x. And then if I take the 121 plus 11 plus 1, I get 133. And that will be my final answer. All right, in the last example, it says find x when f of x equals 20. So all I did right here was just rewrite my function definition that I was originally given. F of x equals 3x plus 11. So in this particular example, we are given that f of x equals 20. So I'm going to plug that in. And then that gives me the ability to solve very easily for x. And that's what we're supposed to be finding. We're supposed to be finding x. So if I subtract the 11, I get 9. So x is going to be equal to 3.